right, so let me just fix my audio here. Yeah, that should be fine. Okay, you can all hear me, right? Perfect, thank you. All right, hello everyone. Today we are going to have our first class where we are going to discuss features. So features are extremely important in computer vision. A lot of the pipelines that we are going to study start with the detection, description, and then eventually matching of features. Even when we study machine learning and eventually deep learning, it all starts with features, which are like ways to describe important characteristics of an image. And then once you have the features, you can do something with them. And there are different ways to find features. This is usually a multi-step process, which we are going to discuss today. I think we are going to have at least 2, maybe 3 classes on features, okay? So let's see how the discussion progresses. And then if we have time, I'll discuss throughout 3 classes features, or maybe at least in 2 of them, okay? So as usual, I would like to start by acknowledging with respect the Lakwangan peoples on whose traditional territory the university stands, and the Songhees, Esquimalt, and Wasanich peoples whose historical relationships with the land continue to this day. The lecture structure today is going to be the following. As I said, we are going to start the discussion of features. We are going to introduce what features are and why what we have up until this point is not enough. So what we have up until this point are ways to detect, doing a very good job actually in detecting edges and image gradients. But for features, we'll see that we can go a step further, okay? So we can be very specific on what parts of the image we want to describe so that this image can be reconstructed later or matched later. We're going to talk about the characteristics of ideal features, its main components. So when we are working with feature extraction pipelines, what are these steps that I was talking about in order to find these features? Measures of uniqueness. And then this is going to be a nice segue to the feature extractor that we are going to discuss today, the Harris and Stephens corner detector. You see in the literature, most of the time, this technique being described as the Harris corner detector. But in other resources, you see Harris and Stephens because, of course, this is the name, the last name of the second author of the paper. So both Harris and Stephens were involved in the original corner detector. So I just thought it would be better to describe this pipeline as the Harris and Stephens corner detector rather than just Harris. So we are going to do a quick review on the mathematics that are involved in the calculation of corners in this particular method. We are going to go over the sum of square distances, the SSD error, Taylor series-based approximation. Of course, we already discussed the Taylor series-based approximation of first-order derivatives in class number 4, if I'm not mistaken. The second moment matrix, interpreting the second moment matrix. So first, we are going to calculate this matrix and then look at its eigenvalues and eigenvectors and see what they mean. Measures of cornerness. We are going to focus on the HS corner detector, but there are other measures of cornerness as well. Invariance and covariance with respect to image transformation. So the last thing we are going to discuss is how robust these features, in particular the corners detected by the HS method, are to these image transformations. Starting with an introduction of features. Features are properties that have been determined important or unique. The process of calculating these features is often referred to as feature engineering. So in other words, we have an image or we have a particular visual class that we want to identify, reconstruct, track. We want to describe these images, this visual information, using key points, using very unique and distinctive points. These are features, okay? And what can be considered as a feature is actually a loose term. So you can consider, for example, that each individual intensity in each pixel is a feature. You can consider that each edge is a feature. You can consider that each corner is a feature. But depending on what features you choose, your methods that depend on features are going to be more or less efficient, okay? The advantages of features is that it can change the dimensions of the problem search space. So I was just mentioning the fact that you could consider that each intensity of a pixel is a feature, right? But that would be a horrible idea, because even for very small images, like a color image of 32 by 32, you would have 32 by 32 by 3 channels features. So more than 3,000 features, you would be working for each image with a feature vector of more than 3,000 dimensions just for this very small image. So for features, we are looking at local characteristics of the images. And then if we do a good job in designing and then extracting our features, we are changing the dimensions of the problem space. Instead of working with 3,000 features for a very small image, we would be looking at just a couple of dozen images, or maybe hundreds of images per image, okay? As the number of features or dimension grows, the amount of data we need to generalize accurately grows exponentially. This is what we call the curse of dimensionality. Again, if we don't do a good job in selecting what our features are going to be, even small images can be described by very, very big feature vectors. And believe me, this is going to be super problematic when training classifiers, for example, or when reconstructing images like this. The ideal characteristics of these features that we are looking like are the following. We want to find features that are invariant to image transformations, in particular, geometric invariance. So for translation, rotation, and scale, we want to find these features before and after these geometric transformations. And also photometric transformations, we discussed those, right? So if we change the intensities of each individual pixel, such as brightness and exposure, we want the features that we calculated before to be related to the features that we are calculating after. Just another example on why just choosing intensities as features for your image is really a bad idea. For a 100 by 100 image, the feature space would be 10,000 of dimensions. So if you have a 100 by 100 image and you consider that each pixel, in this case, a grayscale image, right? That each pixel intensity is one position of the feature vector, you would have a 10,000 dimensions vector. And if this image, for example, possessed a lot of little images, how would each image be distinguished? So it would be just really not a very good idea. Actually, in assignment 3, I'm asking you to, of course, the assignment 3 was not released yet, but it is going to involve that. I'm asking you to extract features using different pipelines, different methods, and one of them is actually considering that the intensities of each pixel are a feature. And you see that after training classifiers that, given these features, are doing image classification, if you use the intensities, each particular intensity as a feature, you see that the performance is not as good. And then we are also going to calculate features coming from SIFT, which is a method we are going to discuss Thursday, and also consider that the hue channel is going to be a feature as well. That's not a very efficient way to do it as well. So the idea of assignment 3 is to show you that based on what you consider to be a feature, your performance on methods that depend on these features are going to change drastically. The advantage of local features. So instead of considering global features, again, this worst case scenario where each intensity is a feature, rather than that, we are going to look at local features and what are the advantages. Locality, features are local, so robust to occlusion and clutter. So if we are calculating, for example, the features necessary to identify a dog, maybe there are a lot of features on different parts of the body of this dog. And even if there's a dog in another image that has got occlusion or a lot of clutter around it, if we are able to calculate some of the features, we are still able to match with the original reference with the image of a full dog, okay? Quantity, hundreds or thousands in a single image. So instead of working with 10,000 features for an image that is super small, 100 by 100, we reduce the total number of features by just a couple of hundreds or maybe thousands of images per image, of features per image. Distinctiveness. Using these features, using these local features, we can differentiate a large data set of objects. So if you calculate good features from a certain visual class, again, the example of a dog, you can then look at 10,000 images at a time and then calculate the features from each individual image and then try to match with these features that you calculated from your reference, okay? So you can differentiate a large data set of objects. And if the features are well designed, and these pipelines that we are going to discuss today and Thursday are very well designed, they are efficient as well. So real-time performance is now a possibility. It's achievable. Features are used for a number of things: image alignment, 3D reconstruction, motion tracking, object recognition, indexing and database retrieval, as I just illustrated, robot navigation, and others. So features are used for a lot of things. To classify the quality, the perceived quality of an image, you can calculate features. To see how well an image enhancement process was, you calculate features before and after, and then compare the ratio. So features are all over the place. They're extremely important, of course. The typical pipeline of a feature extractor is going to follow these steps. The first one is to detect these features. This is actually what we've been doing so far. We are finding the interest points of an image. So an edge is an interesting point of an image. A corner is an interesting point of an image. If we have a near constant region, that is not as interesting, of course. So interest points can be considered to be different things. As I said, we already know how to calculate some of them. For example, edges. Today, we are going to find how to calculate corners. Then once we calculate these interest points, we have very robust way to describe them. So to describe what is their orientation, we are going to discuss on Thursday as well, the histogram of oriented gradients. So it starts by detecting interesting points and then describing each of them in a very unique way. Okay, so that's usually step number 2. And then once you have the interest points well described, you can match them across images, or you can reconstruct this image other way. Okay, so that would be a third step. So we are going to match corresponding features or similar groups of features. For example, for image classification, this is what you are going to do on assignment 3. You are not matching one feature at a time particularly, but if you calculate, for example, that in the image of a dog, you have 30 features, and then you receive another image, and out of these 30, you were able to match, I don't know, 15 or 20, you set a threshold, you can say, okay, there's definitely a dog in this image as well. So that would be the third step. And aside, that's an optional one, but it's quite common as well, is to do feature tracking. So you calculate the features, maybe you match them to an object, and if you're receiving these images in a video, so you have subsequent frames, you can try to track where these features are going, therefore tracking the movement of the object. Okay. So this is an illustration of what I was just saying. First, we have detection. This is what we are going to focus on today. In this image here, for example, of this mountain, we have a lot of interest points. And then the descriptor is going to get one or a group of points and create a feature vector for just this group of points. If we are considering a small area, that looks like the histogram of oriented gradients, for example, as you are going to see. Actually, in the histogram of oriented gradients, you are already implementing it on your second assignment, okay? And as you see, it is going to consider a window of size. For example, the standard is 8 by 8, okay? So yeah, you describe the interest points that you just calculated. So you could describe them here and then describe them here as well. And once you have this description, so you identify, you describe them, and now you can match them, okay? And this is what it is illustrated here. All right, so what makes a good feature? What part of the image should we look at in order to then do the description and eventually matching? Let's consider this image here and 3 different points of this image. So point D is this one here. Point B, so point D is a near constant region, and we are calculating for each point in this patch. So consider a, I don't know, 9 by 9 patch or 11 by 11. In each point, we are calculating the intensity of the gradient, considering X and Y, okay? So in this point, since the intensities are all over the place, there's not quite a constant pattern that is being formed in this image of the gradients, okay? If you look at this other region where you have the edges of the roof of this house, you are definitely going to see an edge that looks like this, because of course, between the roof and the background, which in this case is the sky, you have a very clear change in intensity. So the edges look very clear here. But the problem with these edges, they are interest points, okay? So you could consider them to be interest points, but they are not so unique, because if you go from this point, for example, to this point, or maybe this point, the profile of the gradient that is being created is going to be extremely similar. So just given this profile, it would be hard for you to tell where it came from. So even though edges are definitely interesting points, they are not necessarily so unique. And then if you look at this flower bed here, you see that there's only one point that possesses gradients in both X and Y. So in these kinds of points, you would have a more unique location, a more unique representation of local characteristics of an image. But we'll discuss that a little bit more, okay? We are going to look for image regions that are unusual. So edges are interesting, but they are not that unusual. Lead to unambiguous matches in other images. That's the idea. Again, edges are nice, but they are not so unique. So it's hard to have an unambiguous match in other images. How to define unusual? Look at the gradients in different orientations. That is going to be the theme for this whole class. So let's consider these three regions, okay? Suppose we only consider a small window of pixels. What defines whether a feature is good or bad? So is it a good candidate or is it a bad candidate? So what we are going to do is to consider just a window of the same size. If this window is positioned here, the idea is going to be, we are going to move this window just a little bit in the x-axis, which we are going to describe as U. So U could be 1 pixel, for example, okay? So just a little bit on the x-axis and just a little bit on the y-axis as well. The displacement on the y-axis is going to be described as V. So we are going to move U and V a little bit, okay? If we do this movement on this flat region, and then we subtract the value of all intensities put together. So we start with a window here, and then we move it a little bit. So for each pixel position, we are doing the first one minus the corresponding one. The second one minus the corresponding second one, et cetera, et cetera. If the intensities are not going to change and we do this subtraction and then sum all of them together, we are not going to see a lot of displacement, a lot of error, okay? If we do that in an edge, what is going to happen? Well, if we are in this edge in particular, if we move on the y-axis, we are going to see no change at all. And if we move in the x-axis, now we are seeing a little bit of an error. We are seeing a little bit of a displacement, okay? But if we are in a corner, what happens is that regardless of whether we're moving in the x-axis or in the y-axis, in both these displacements, we are going to see some error when we subtract the first window by the second one. So this is the idea that we are going to now develop throughout this class, okay? So we are going to calculate the amount of error based on the first window and the second window, the contents of the first window and the contents of the second window. If we are in a corner, this error is going to be maximum. All right, so how can we calculate this mathematically? So this is the segue to the Harris-Stephens corner detector. This is what they are trying to do. By the way, that was proposed in 1988. And in order to do that, we are going to calculate the sum of square distances between these two windows, okay? So we are going to consider shifting the window W by U and V. As I said, U represents a displacement in the x-axis, V a displacement in the v-axis. So we start with W, and then we change its position just a little bit, U and V. And by the way, U and V are typically going to be 1 pixel, okay? But the idea is we start with W, and then we change it by U and V. As we said, if we are in an edge, we are only going to see displacement based on one of the axes. And if we are in a corner, any x is going to generate displacement, okay? How do pixels in W change? Compare each pixel before and after by summing up the square differences, the sum of square differences, SSD. The definition of SSD error is the following. It's actually quite easy. We have all the pixels inside of a window W, okay? So X and Y are just 1 pixel position inside of W. If W it was 3 by 3, we would have 9 different positions for each window. And then we are going to add this little displacement that can be 1 pixel, 2 pixels, etc. We usually consider that to be small, so just 1 pixel. And then after adding this displacement, we subtract on a pixel-wise manner the new intensity value by the old intensity value, okay? And the reason why it's called the square is because you have, of course, to the power of 2 here. We are happy if this error is high, of course, because if we are in a corner, by moving it a little bit and then summing the square differences, this error is going to be high. So we are happy if this error is high. It is slow to compute exactly for each pixel and each offset UV. So you could definitely do that for each pixel on each window, and you could center these windows in all positions of the image. That's a possibility, but no one is doing that because this is not efficient, okay? So instead, we are going to use a Taylor series to approximate the value of this function here, and you see that there are a lot of nice things that we can get from this approximation, okay? So this is what we are trying to approximate. Again, you could implement this algorithm right away with this form, but this is not efficient, okay? So this is going to be a little review on what we discussed on lecture 6, the Taylor series expansion. Taylor series can be used to approximate a function at a certain point. We already know that, using derivatives and polynomials of increasingly higher order. So if we want to approximate this function here, this is how it's going to look like. In fact, this is similar to what we approximated on the last class, sorry, on lecture number 6. We start again by looking at the 1D version of this approximation. So if we have a function, in this case, we are already working with a discrete function, so an image. So an image x plus a little bit of a displacement of u. This is going to be ix plus the derivative of the image with respect to x times this displacement here, u, okay? Plus higher order terms. As we know, if we add higher and higher order terms, the approximation is going to get better and better. But this is not necessary, just these two terms are more than enough. And then if we consider the 2D version of this approximation, it's going to be super similar. We just have to look at the value now in this coordinate x, y, okay? And then sum with the derivative with the image with respect to x times whatever displacement you have in x, and same thing for y, okay? And then we can assume that we are working with small motions, okay? And if this is the case, this is exactly the formula that we have in the end. The value of the image in this particular point plus the derivative in x times u, the derivative in y times y, okay? Very good. So instead of working with the derivative of the image in x and the derivative of the image in y, we are going to use a shorthand representation, which is ix and iy. So whenever you see ix, it represents the derivative of the image with respect to x in the x-axis, right? And the derivative of the image in y, it's going to be iy, okay? Very good. So now that we have a very good approximation of this function here, we are going to substitute its value in the original SSD formula. So we start with a formula that looks like this, with an equation that looks like this. And then we substitute this by the value of the pixel where we are looking at right now in position x and y, plus the derivative of the image in x times u, the derivative of the image in y times v. Very good. As you can see, we can cancel these two terms here. So we cancel them out, and we are left with an approximation of the SSD error that looks like this. Derivative in x u plus derivative in y v squared. So what we are going to do is then to just expand this. Let me see if I have anyone in the waiting room. No? Okay. So what we are going to do is to expand this equation here. All right, so of course we have the first term squared plus 2 times the first and the second term plus the second term squared. Very good. So I just expanded this equation here. And now we are going to consider that the summation in this first part is A, the summation in this second part is B, and the summation in the third part is C. Okay, so just the same equation represented using these shorthands A, B, and C. So this is how your equation is going to look like. Therefore, your error your sum of square distances error is locally approximated as a quadratic error function. So as a quadratic function like this one, okay? And then when you're studying the HS corner detector, you see that they now go from this representation to a matrix form. So this is what this slide is all about. So usually they show the quadratic approximation of this error and then the matrix form. So instead of doing that, I wanted to have a step-by-step process here so that you know exactly why we went from this version to this version, from this representation to this representation. By the way, we get to this representation because of the eigenvalues and eigenvectors of this matrix. So this is going to make a lot of sense, but let's go again step by step. So we start with this quadratic form for the approximation of the error, okay? And then we are just going to expand this term here to BUV. So this is going to be BUV plus BUV, very good. And then we put the UV outside. So if you want to know why are they same, you can see that if we multiply this term by U, we're back here. And if we multiply this term by V, we're back here. Very good. And then we do the same thing with the term that is remaining here. So UV on one side and UV on the other side. So we actually isolated the UVs. Very good. So this matrix that we created here is going to have these two terms being the same. We are going to look at this form, okay? But these two terms are the same and these two terms are different. This is an extremely important matrix. This is what we call the second moment matrix. In different literature, you are going to see this matrix being referred to as different things. So second moment matrix, sometimes Harris matrix, sometimes the H matrix, sometimes the M matrix. So it's all over the place, but they all refer to the same thing, okay? If we substitute the values of A, B, and C that we had here in this matrix, this is the form that the matrix is going to take. Of course, we're taking the summation outside, so the summation is here, and these are the terms of this matrix. So let's look at these terms specifically. We have the derivative in x times the derivative in y, the derivative in x squared, the derivative in y squared. So how can we get to these terms? We actually know how to do that. We start with an original image to find the derivative in x. We know that there are very easy approximations to get there. We can use the operators that we discussed so much, right? So the Pruitt's operator, the Sobel operator. So with the Pruitt's or Sobel, as you know, it's better to use Sobel most of the times. We can get to y of x and y of I of y, sorry. And then if we square this image, we get to this term. If we square this image, we get to this term. And if we multiply them together, we get to these two other terms. By the way, we are going to do this calculation for each pixel in the image, okay? Very good. So maybe now it's a good time to talk about how this window W looks like. So this window W can be calculated exactly like I'm describing right now. You just go to the original image, you calculate the derivative in x and the derivative in y, and then you multiply them, you get to this, representation of the image. Very good. But if you just go ahead and do that, the results are not as good. In practice, we typically use a simple window W. Just using, a simple window W doesn't work too well. So what is typically done is that we'll weight each derivative value based on its distance from the center pixel. In other words, we are going to multiply this representation of the image by a certain kernel. It can be a box kernel or it can be a Gaussian kernel, okay? So we are going to add this extra term here, okay? Again, this is not a mandatory thing, but this is usually done when calculating corners. So let's just consider that we're doing that for the rest of the discussion. When you multiply this second moment matrix with this Gaussian kernel or box filter, for example, this is what we call the Harris matrix. Oh, I have someone here in the waiting room. Okay, so again, just wanted to mention that this is not a mandatory thing, but this is usually done when calculating the corners. So let's just consider that we're doing that. In particular, when are you going to use the window or the Gaussian kernel? Okay, the window kernel or the box filter is used when computational speed is critical and the noise level is low. So if you don't expect your input image to be super noisy, you can get away with just multiplying this matrix by a box filter. That would be enough. But if you expect your image to be noisy, you want first to smooth the image and then to calculate these errors that we're talking about. So the exponential form, the Gaussian filter, is used when data is moving, is important, okay? Very good. So now let's go again to this matrix, this very interesting matrix. As I said, it goes by a lot of different names. It can be referred to as the matrix H, the second moment matrix, the Harris matrix. In a lot of references, it's referred to as M. They are all talking about this particular matrix here, okay? Which we know the form. So who is A? A is the derivative of the image in X squared. Same thing for B here, same thing for C here, okay? Very good. This matrix is going to tell us how much the error is changing in both displacements, in the displacement of U and in the displacement of V. So it's very important that we understand its form. So let's try and understand what its shape represents. If we have a region where there's no error, if we do some displacement in U, for example, so if we're moving this window horizontally, the error is not going to change, okay? So in this case, if the error in X is not going to change, the derivative in X is 0, okay? So this term is 0, same as this one and this one. The matrix looks like this. And then this 3D representation of the error with respect to the displacement in X and the displacement in Y is going to look like this. Of course, if we change the values in X, so if we change the displacement in X, the error is going to be exactly the same, and it is going to be given actually by the displacement in Y. So in this case, only the displacement in Y is important, right? Very good. And if we move to this other position on this image, we'll see that now the displacement in X is the important one. Of course, if we change the value of the displacement in X, meaning the U parameter, the error is going to change accordingly. But if we change for a given U, the value in V, now the error is going to be exactly the same. Very good. So just looking at the form of this graph, we can tell if we are on an edge, if we are on a flat region, or if we are on a corner, which is what this slide here is all about. If we are on a flat region, the error is going to look flat as well, a flat surface. If we are on an edge or on the edges that create a line in particular, this is how it is going to look like. This is what I was discussing just now. And if we are on a corner, it is going to look like this. Actually, in the beginning of the class, when I was showing you this image, so let me go back here just a little bit. Yeah, so this image here, these representations, these graphs are actually this error graph that I'm discussing right now. So now they make more sense, right? Okay, so let's go back here. All right, very good. So first, I wanted to give you a visual understanding of what these graphs are all about. But of course, we are not going to look at this graph for each pixel and then decide if this is a corner or an edge. This is going to be done automatically. So now I want you to consider this property. The eigenvectors of a real symmetric matrix, and by the way, H is exactly that. It's all formed by real terms, and it is a symmetric matrix. So this property holds for H. Point in the direction of maximum data spread. And the corresponding eigenvalues are proportional to the amount of data spread in the direction of the eigenvectors, okay? So let's look at generically how that is represented on this error surface, and then specifically for H, okay? So generically, if we have a patch with a number of pixels here, and we calculate the derivatives in X and the derivatives in Y, and then plot for each point inside of this window here, and let's say that there are, I don't know, 30 points inside of this window, and for each of them, we are calculating the displacement in X and in Y. If we are doing that in a relatively flat region, they actually added a little bit of Gaussian noise just so the representation is better. So it's not exactly flat, but it's almost flat, this region here. All the error is going to be concentrated in the middle, close to the origin, okay? This is going to be represented by small eigenvalues on the ellipse that fits this data, okay? we are going to look at this. We are going to look at this idea on their different views. Okay, but if we fit an ellipse around this, these points, they are going to look like this. Sorry, the ellipse is going to look like this. And as we said, the eigenvalues of this ellipse are going to tell you how big are the major and minor axes, and the positions where they are is going to be given by the eigenvectors. So eigenvalues, the size, eigenvectors, the position. Okay. If we go to an edge now, what is going to happen? Well, on an edge, we are only going to see displacement in one direction. And then if we fit an ellipse here, you see that, again, eigenvalues are the widths, right, of the major and minor axes. So there's definitely a huge eigenvalue here and a small eigenvalue here. So we have a large and a small eigenvalue. If we just look at the eigenvalues, edges are always going to be represented this way: a small eigenvalue and a large eigenvalue. If you are on a corner now, your ellipse is going to look like this. So both eigenvalues are big and they are relatively similar in absolute value as well. Okay, so if we are just looking at the eigenvalues, a corner is going to be characterized by two large eigenvalues. Very good. So now let's go back to the specific matrix we're working with, matrix H. We have this property here. We know that this matrix H is representing the error plane. Okay, so this 3D graph that represents the error based on the displacement in X or in Y. Now I want you to consider that we are setting its values to be constant. So we are just getting a slice of this plane. This slice, as we just seen in this image, is going to look like an ellipse. And this ellipse, again, now talking specifically about ellipse H, is going to have, we can visualize H as an ellipse, okay, with axis lengths determined by the eigenvalues of H, very good, and the orientation determined by the eigenvectors of H. So as we said, in this case, for example, in this representation, we can see that there's a very large eigenvalue here and a relatively smaller eigenvalue here. So we are probably looking at this representation to an edge point, the edge that is forming a line, okay? Very good. So it is in, oh, I think I have a question. What is the difference between a corner and an edge? Is it that important that a corner is just the turning point of an edge? I think I actually got it. The corner is just the point where two or more edges meet, correct? Yes, so what happened, Cristiano? So the main difference between an edge and a corner is that, let me go back to this image here. This one, okay. So the main difference is that for edges, if you change the position of this window, so if you change the displacement of this window in one axis, for example, here in the y-axis, the intensities inside of this window are not going to change. If you are in another edge, a horizontal one, if you change the position of the window in the x-axis now, the intensities are not going to change as well. What happens in a corner, which is very particular to a corner, is that if you are here, so in this case here, any displacement that you do in either X or in Y is going to generate a lot of error. It's going to generate a lot of differences between the original intensities and the new intensities, okay? So the difference between an edge and a corner is this one. For an edge, just the displacement in a particular position is going to generate error, while in a corner, any displacement in any position is going to generate a lot of differences, a lot of error, okay? Very good. So let me just quickly check the time. Okay, I think we have enough time. I wanted to give you a very quick review of eigenvalues and eigenvectors, because I know that this is not necessarily the favorite subject from most students in linear algebra. So a very quick review. Eigenvectors of a matrix A are the vectors X that satisfy the following. So it's super interesting what they do. If you multiply your matrix with a particular vector, what is called the eigenvector, in the result, you're going to have another version of the same vector multiplied by a constant. So this vector is called an eigenvector, and this constant is called its eigenvalue. And if we had more time, we could discuss visually what they represent, but this video does a great job in illustrating these concepts. This is from a channel called 3 Blue 1 Brown. Okay, so I recommend actually everything from this channel, and this video in particular is super illustrating. It shows that what we're doing here is that if you are multiplying this matrix by this vector, you're actually changing the basis of this original matrix here, but the new vector that is being created is not being knocked off this new representation. Anyways, this is out of the context of the class, but I highly recommend this video, okay? It's just 17 minutes, I believe. The scalar lambda is the eigenvalue corresponding to a particular eigenvector, okay? And the eigenvalues can be found by using this equation. We actually worked with this one in the first assignment, so you remember how to do that. With a quick example of a 3x3 matrix, we start with this matrix here, and if we use this equation, we are going to subtract this matrix by lambda identity, okay? So this matrix minus lambda identity is going to be the following: -1 minus lambda, 3 minus lambda, 7 minus lambda. The other terms will not change, of course. And to find the determinant of a 3x3 matrix, remember how to do that. There are multiple ways actually to do that. One of which is going to be just expanding this matrix, a representation of this matrix where the first two columns are reproduced. And then you multiply all these terms, sum with the multiplication of all these terms, sum with the multiplication of all these terms, minus all the ones that are in red. Very conveniently, this matrix is going to have all these terms 0, except this first multiplication. Okay, so it is going to look like this. And since we are working with a 3x3 matrix, so since we had 3 different eigenvalues, we are waiting for 3 different intensities, 3 different values for these eigenvalues, okay? In this case, it's super easy. It's not always going to be that easy to calculate them, as you know from assignment 1. So in this case, we have eigenvalues 7, -1, and 3, okay? So pick one eigenvalue, and as I said, there's going to be an eigenvector corresponding to it. In fact, an infinite amount of eigenvectors corresponding to it. Each eigenvalue determines an infinite number of non-zero eigenvectors. Okay, so for our discussion, let's consider the eigenvalue -1, which we just calculated here, okay? First, we go back to the original equation. So there's something funky about this equation if you stop to think about it. We have the multiplication of a matrix and a vector in the left-hand side. And on the right-hand side, we have the multiplication of a constant and a vector. So just to make things, just to do a little bit of housekeeping, we are going to add the identity matrix, which is not going to change things much here. But now we have matrix, vector, okay? And then we send this term to the left-hand side and we isolate x. This is how it is going to look like. Okay, so this is the formula that you use once you know your eigenvalues, and then you want to find the eigenvectors. Again, we are going to consider the eigenvalue -1, just to make things easier. So this is how this part of the equation is going to look like. And of course, your eigenvector is going to be 3x1 column vector, like this one. So this is going to generate a system of linear equations, very easy to solve. You have 3 equations and up to 3 variables. As you can see, x1 does not appear in any of these equations. So it can take any value that you want. Let's start with x3. x3 is going to be 0, therefore this is 0, and then x2 is 0 as well. Let's just consider that x1 is 1. So this is one eigenvector for this particular eigenvalue, for the eigenvalue -1. If you add this 1, 0, 0 to this equation here, you see that A times this eigenvector, 1, 0, 0, is going to result in the same eigenvector multiplied by its eigenvalue, which we already know is -1, okay? The reason why I say that there's an infinite number of such vectors is because if you multiply this eigenvector by any constant that you can think of, this is also going to be an eigenvector on the output, okay? And the reason why I say non-zero is because 0, 0, 0 can always be considered an eigenvector, but it's a super boring one. It doesn't tell us much about the equation. So typically we don't consider the 0, 0, 0 eigenvector, okay? Very good. So now we already knew, right? But we were reminded on how to calculate eigenvectors and eigenvalues. But as you know, for our matrix H is a 2 by 2 matrix. It's not a 3 by 3 one. So things are even easier. If we consider now our 2 by 2 matrix H, the determinant, so this equation here, determinant of the matrix minus the eigenvalues in the main diagonal, this is how it is going to look like. So term 1, 1 minus one of the eigenvalues, term 1, 2, term 2, 1, and term 2, 2 minus the other eigenvalue. So the formula to find these eigenvalues is always going to be the same. It is always going to be this one. As you can see, there are a couple of things that we're doing here. We're doing a square root, and we are doing power of 2 as well. So the computational cost of a square root in power of 2 is higher, for example, than the computational cost of a sum or a simple multiplication. So let's just keep that in mind, okay? Because this is going to play an important role in a discussion that we are going to have in a few moments. Once you know the eigenvalues, you can find the eigenvectors by solving this equation as we just illustrated in the example. Very good. So finally, again, we're back to the interpretation of the eigenvectors and eigenvalues. We already know exactly what matrix H looks like. We already know how to calculate its eigenvalues and eigenvectors. By the way, we are not going to go to the eigenvectors. The eigenvalues are the only things we are interested in right now. Okay, so we have one H, and then we have two eigenvalues. If one of the eigenvalues is extremely large in comparison with the other one, that means that we are generating error in just one direction. What does it mean? We already know. That means that we are on an edge. If the other eigenvalue is extremely high in comparison with eigenvalue, so if eigenvalue 2 is way higher than eigenvalue 1, so the other way around, we are again in an edge, but now an edge that is horizontal or an edge that is vertical, okay? So regardless if one eigenvalue is considerably higher than the other, you are in an edge. If you are in a flat region, it doesn't matter where are you moving. The values are not going to change much. So the error, the SSD error is not going to change much as well. So in this case, the eigenvalues are both going to be small because again, remember what they represent. The eigenvalues represent the size of the major and minor axes of the ellipse that is feeding the data. So if the data is not changing much, the ellipse is small, therefore its axes are both small and the eigenvalues are both small, okay? So both eigenvalues small, we're talking about a flat region. If one of them is considerably higher than the other, an edge region. And if we have a corner, as we just discussed as well, both of them are going to be large. Why? Because both the minor and the major axes of the ellipse that is feeding the data are going to be considerably big, okay, considerably large. So now we know what to look for in an image in order to find corners. So that is going to be kind of a version 1 of the algorithm, of the approach, okay? We already know that the eigenvalues are going to give us the amount of increase in each direction, in X and Y, and the eigenvectors are going to tell us where this direction is happening, okay? All right, so now what is going to be our, sorry, just give me one quick sec. Okay, so now what is going to be our scoring function? We already know what the eigenvalues represent, and we want to find a systematic way, a function that is going to consider the eigenvalues, and based on its value, it's going to tell you if this is a corner, if this is an edge, etc. Very good. So the idea here is that we want the error to be large for small shifts in all directions. Right, this happens in a corner, right? The minimum of the error should be large over all unit vectors. So regardless if you're moving in U or in V, meaning in X or in Y, you want the error to be large. This is what characterizes a corner, as we know. This minimum is given by the smaller eigenvalue of H. So this is a slightly different way to look at it. Let me go back here because it's going to make more sense. What happens in a flat region is that both eigenvalues are small, okay? So both small, not a problem. If you are in an edge, one eigenvalue is going to be super high and the other one is going to be small. So the smallest eigenvalue in this case is small. The smallest eigenvalue in this case is also small. The smallest eigenvalue in the other edge, again, is going to be small. But if you are in a corner, the smallest eigenvalue is going to be relatively large. So the only position where the smallest eigenvalue is going to be relatively large is in a corner. So this is what this original idea is looking at. We are going to consider, for example, this image here. The largest eigenvalue is going to, of course, represent the change in the positions where you have the most, in positions where the gradient is higher. So for example, in the x-axis here, you have a lot of change. So this eigenvalue is going to represent the change in the x-axis. Of course, it is going to be super high in all these positions. In this one, we are talking about the displacement in y, in this one, the displacement in x, but regardless, the maximum eigenvalue is going to be very large for all these positions. But the idea that only in corners, the smallest eigenvalue is going to be high is shown here, is illustrated here. Okay, so only in these corners, both the highest and the smallest eigenvalue are going to be relatively large. Very interesting, right? So the idea here, the algorithm, the pseudo algorithm would be to compute the gradient of each point in the image, then compute the H matrix, compute the eigenvalues, and then interpret these eigenvalues. We are going to find points with large response, which are represented by positions where the minimum eigenvalue is higher than a certain threshold. And then if we have multiple, we are just going to choose the local maximum. For example, in this corner here, this is the value of the smallest eigenvalues, right? So since we have smallest eigenvalues with relatively high values all around the place, we know that there's a corner here, but what is going to be its specific position? Well, the local maximum. So if we consider, for example, a window here, we just grab the highest value. This is going to be your single point of a corner, okay? So that's like a first version of the HS detector. The problem is that, as I said, the calculation of specific intensities of eigenvalues 1 and 2 involves the calculation of a square root. It involves a square term here. So this is computationally expensive. That's the reason why in the original paper of the HS corner detector, calculating absolute values of eigenvalues is computationally expensive since it involves the calculation of a square root. Very good. So in the original paper, the authors replaced the eigenvalues calculation with less expensive operators. So everything we said so far makes total sense, and you could go ahead and calculate those. But in order to be a little bit more efficient, what the authors did was to consider two very interesting properties from linear algebra. These properties hold for all square matrices, okay? So the trace, meaning the sum of diagonal elements in our trace H, A plus C, okay, of a square matrix is equal to the sum of its eigenvalues. So instead of calculating the actual eigenvalues, which as I said is computationally expensive, we already know that the sum of their values is going to be given by just the trace of our matrix H. A second property says that the determinant of a square matrix equals the product of its eigenvalues. So now, without calculating the actual eigenvalues, we know what it's their sum and what it's their multiplication. Very interesting, right? Then the HS detector continues to define the measure R to analyze the changes in intensity, meaning the eigenvalues of the function. We discussed that at length, based only on the trace and the determinants. So they are looking at this relationship, the multiplication of the eigenvalues minus their summation. But instead of calculating their actual values to do this calculation, to calculate R, they are just looking at the determinant of the matrix and the trace of the matrix. Very good, right? So computationally, it's way, way more efficient to do that. By the way, this K here, this parameter K, you can think of it as a sensitivity factor. The smaller it is, the more likely the detector is to find corners. So it becomes more or less sensitive to what it considers to be corners. So that's the first thing we do. The second thing we do is that in order to consider that a certain R represents a corner or not, we are going to compare it typically with a threshold, okay? So we have to set a K and a threshold in order to determine if we just found a corner or not. And then how can we interpret R? Because we were talking about the eigenvalues, right? What about R? Well, the interpretation of R is going to be quite similar to the one in the eigenvalues as well. So for edges, R is going to be extremely small. So both edges in the vertical or horizontal direction. For flat regions, the absolute value of R is going to be small. And for corners, the absolute value of R is going to be large. If you look at how the eigenvalues would look like, that makes a lot of sense. So for example, for corners, since corners are characterized by both eigenvalues being super large, the R is also going to be large. If you are looking at an edge, on the other hand, so for an edge, let me see here. Yes, so for edge, you have one large and one small eigenvalue. When you do the multiplication of them, minus K times the sum of them, you see that the value is going to be negative, a very large negative value, okay? And if both of them are small, well, then their multiplication minus their summation is still going to be a small number. So this is the interpretation of the R value. Instead of interpreting based on the values of the eigenvalues, we're interpreting based on the value of R, okay? Very good. So this is an interesting example that shows that if you change the values of K and the threshold, you can get to different results. So the behavior of your corner detector is going to change slightly. You start with an image like this. It is again plagued by a lot of Gaussian noise. As you can see, the intensity of the changes on the left-hand side are a little stronger than on the right-hand side. So this is going to be important. If you start by calculating the corners using K equals 0.004 and the threshold equals 0.001, you see that all the valid corners are found, but other corners, invalid corners, are found as well. So what the authors did here was to then increase the value of K. So they are making it less sensible to, they're making it more strict to what it's considered to be an edge, sorry, a corner, okay? So this is what it's shown here. So they actually increased from 0.04 to 0.1. So more than double the value of K. And as expected, the number of corners that were detected decreased a lot. Only the valid corners are now found here. And then they continue to do an interesting thing. They are getting to the same result by now fixing the value of K to the original one, the same one that they use here, and then changing the value of T. So that shows that depending on the values of K and T, you have a lot of liberty to determine what is the behavior of the detector. And then finally in this one, they are increasing a lot the value of the threshold. So only the strong corners are now left in the output. And as you can see, as expected, actually, these corners are the strongest ones because the difference in intensities in this side of the image are stronger than on the right side of the image. So that's why you see corners here, 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 and in these two positions as well, okay? So this image shows exactly the same thing. So they're just playing around with the values of K and T. And it's interesting to see that if you change the sensitivity plus the threshold, the behavior of the detector is going to be completely different. We already discussed the fact that just by looking at the value of R, we can determine rather, if this is an edge, if this is a corner, or if this is a flat region. The other thing that I would like to mention is that this measure, sometimes called, since we are talking about corners, the measure of cornerness, is particular to this paper, the HS corner detector. But there are other ways to relate the values of the eigenvalues, right? So there are other measure of cornerness, other functions that show that based on the values of eigenvalues, okay? So we were just discussing the one from the HS corner detector, but Kanada and Tomasi in '94, for example, consider that, okay, we are going to calculate the values of these two lambdas, right? So eigenvalue 1 and 2, and we are going to look at the minimum out of them. This is the analysis that we were doing here, right? So this is what they did in this paper from 94. Noble actually uses the determinant in the trace again, but in a different way. As you can see, it is not just subtracting the determinant by a parameter times the trace squared. It's actually looking at the ratio plus a parameter that can be set, multiplying by 2. Triggs, again, look at the absolute values of lambda 1 and lambda 2. And Brown, Slezinski, and Winder, you might remember that Slezinski is the author of the book that we referred to a lot during this course. They proposed to just look at the ratio between the determinant and the trace. The interesting thing about their method is that they are not using a K. So this is one less parameter that you have to fine tune. Very interesting. Okay, so if we look at a visualization of how these are parameters look like, sorry, as these are functions of cornerness look like, if we calculate R for this image, which by the way is the same object, but now rotated and with different intensities, we are going to look in red, the regions where the R has got a high value, and in blue, the region where R is actually very low. As expected, in these near constant regions, the R is going to be low, so all blue. And for example, in the neck of the zebra, we can see a lot of high values for R. Why? Because the intensities are changing in both X and Y, okay? Very good. And then of course we apply the threshold. So now we have a binary image where only positions with values higher than this threshold are considered to be 255, to be white, all the other ones are black. And then if we find the local maxima of F, again, we want single positions for edges, not a bunch of positions. So if we consider local maxima of F, in this representation, F is the cornerness measure R. This is what we are left with. And then if we superimpose all these positions in the original image by painting them red, this is what it looks like. So all these red dots were considered to have a high R. So they can be considered as corners, okay? Why are the corners of the tiles close to the border of the image not detected as corners? So let me see. What was the image, Cristiano, that you were referring to here? Why are the corners of the tiles close to the border of the image not detected as corners? So maybe it was this one. Yeah, I will assume, Cristiano, that you're talking about this image here. Okay, so the reason why these are not considered to be corners is because the window is not shifted up here, because then you would have to pad the borders with a constant value or with a reflected value, things of that nature. Same thing goes for the left-hand side and probably for the bottom of the image as well, right? Yes, the bottom of the image as well. Yeah, just because you can't move they consider that you couldn't move the window up or down, okay? All right, so let me see how much time we still have. Very good, we have 70 minutes. Okay. So this is it for the mathematical discussion on the HS corner detector. I wanted to put this slide here as a summary of all the steps that we need to do. And it's actually super easy. And I recommend that you try and implement this because it's straightforward, but the method is super interesting, right? You start with an original image. You can blur the image first. The reason why you blur the image is if you have an impulsive noise. So if you have, for example, all black in a certain region of the image and just a speck of white, if you center a window that is around this particular point, if this window moves a little bit, there's going to be a considerable amount of error there. So this can be considered as a corner. So in fact, a single point can also be considered as a corner, okay? This is not necessarily what you want your algorithm to detect. So in order to mitigate a little bit this behavior, you could blur the image first. Again, not a mandatory thing, but a common step to follow before starting the processing. All right, so we first blur the image, then we use a certain operator to find the derivative in X and the derivative in Y. We already know that we can use Pruitt to do that. We can use Sobel to do that, for example. And then in order to find the matrix H, we only need to square this image and square this image as well, and then to multiply them. We have all the terms. So the derivative of the image with respect to the x-axis here, the derivative of the image with respect to the y-axis here. If we square this one, we get this image. If we square this one, we get this image. And if we multiply both of them, we get this image. So all the terms for the matrix H. The next one, as I said, is a very common step where you are multiplying this representation of the image. So you are multiplying each of these by this particular kernel. So you are applying, for example, convolution of this kernel, a Gaussian kernel, in all these images. So you are blurring these images. Very good. And then finally, you calculate the cornerness function. Both eigenvalues are strong when you are looking at a corner, okay? So as I said, not necessarily only classical corners are going to have a high R. If you have individual points like these three here, they are going to have high corner values as well. They're going to have high R's as well, okay? So just keep that in mind. And then finally, we do no maximum suppression in order to reduce this group of pixels that had an R and are close together to just a single position, okay? That will be the last step. And again, if you just want to remember how to implement or how the HS corner detector works, you can come back to this slide here and everything is summarized. Very good. So the last thing we need to discuss in this class is how invariant these corners that we found are to image transformations, in particular geometric transformations and photometric transformations. For geometric transformations, for example, we're talking about rotation. In this image of a bee, we start with an image like this, we rotate it a little bit. With scale, we are looking at different scales of the image. So a zoomed in version of the image, a zoomed out version of the image, and the photometric transformations are going to be the intensity changes. And we discussed how to do these intensity changes, I believe, in lecture number 3. Okay, so let's see how the features react to these transformations. We want features to have invariance and covariance, actually. We want corner locations to be invariant to photometric transformations. So if we find a corner here, for example, in this original image, after changing the intensities of the image, ideally, we would find another corner in the very same position, okay? So this is invariance. But covariance is going to refer to the new location of these same features, okay? So invariant to photometric transformations and covariant to geometric transformations. For example, if we had a feature in the back of the bee here, if we rotate the image, of course, we don't want the same feature to be found in the exact same Cartesian coordinate, but in its equivalent position in the new image, okay? So invariance and covariance. Let's look at image translation. So we are just moving the image a little bit. Well, the corner here is going to be found, the exact same corner is going to be found here, but in its particular new position. So in the equivalent position that we are expecting this same corner to be found in the output image, okay? So the derivatives and window function are shift invariant. The same corners are going to be found, but in the equivalent position after the translation. So we say that corner location is covariant, not invariant. We don't want it to be invariant. In this case, we want it to be covariant with respect to translation. Very good. What about image rotation? If we rotate the image, this is how the ellipse showing the error is going to look like. The second moment ellipse rotates, but its shape, meaning its eigenvalues, remains the same. So we are looking at exactly the same corners with just a different position. So corner location is covariant with respect to rotation, okay? Very good, now intensity changes. As we know from lecture number 3, we can change the intensities in a lot of different ways, but just looking at adding a bias, which is a constant value to all pixel intensities, or multiplying the intensities by a gain. If we first consider the bias, what happens is that all pixel intensities are going to be added or subtracted, for that matter, by the same value. So the absolute difference between these intensities is going to change the same. So since we are only using derivatives and the delta, the difference in intensities is not going to change, nor will the derivatives. So the corners that we find are going to be exactly the same. However, if we do intensity scaling or contrast adjustment, that's what we call it on lecture 3, by multiplying every intensity by a certain value, then the delta, the total difference in intensities might change. Take, for example, a pixel with intensity 1 and a pixel with intensity 10, close to each other, okay? So the original delta between them is just 9 pixels, 9 levels of intensity, right? If you multiply both of them by 10, for example, now you have 10 and 100. So now the difference in intensity is 90. So even though the derivatives follow the same overall pattern, so they have a similar behavior, their form is similar, their absolute values is completely different. So for the same threshold, you find completely different corners. Therefore, we say that they are partially invariant to intensity changes, because it depends on what kind of change you're doing. If it's a constant change by adding a bias, for example, then they are invariant, the corners. If you are now adding a gain, they are not invariant anymore. Okay, so partially invariant is how we are going to define it. And then finally, scaling. If we consider a window of this size and the image is this size here, this is going to be considered as a corner. Very good. However, if we change the scale of this image, so now the image is, say, 5 times bigger, now the same window is going to determine that all these points are edges and not corners anymore. So it's definitely not invariant to scaling. Actually, scaling is really a problem that all the feature detectors try to solve. So let's talk a little bit more about scaling. If we want to find, for example, corners, but that same analysis go to any other feature that you would be looking at, different scales would definitely give you different results. So you have a measure of cornerness, for example, in the detection of corner, this is going to be our function f. What you could do is to center this analysis in each position of the image. And for each position, you could calculate this function f. Again, in our case, it's going to be r, the cornerness at each point, in different scales. And then you change both position and scale. And for each of these positions, you would log what was the scale that generated the maximum f. In our case, the maximum r, okay? Very good. One definition of f could be, for example, the Harris operator, R. And that is it. All right. So that was the first lecture on features. We are now moving towards more, I wouldn't say fancier, right? But for more pipeline-like ways to find features. We are going to discuss SIFT on the next class and the histogram of oriented gradients as well. You know that the second assignment is all about the histogram of oriented gradients. I do believe that you already have everything, all the tools necessary to implement the histogram of oriented gradients. So if you want to go ahead and start the second part of assignment 2, you are definitely good to start doing that. If not, if you feel more comfortable in discussing this algorithm first, then you can wait up until Thursday, and we are going to see how HOG looks like, okay? Very good. So let me see. Okay, so Wilson asks, how would aliasing affect corner detection? Okay, so it would definitely affect corner detection, right? Because when you have aliasing, it can, for example, break down lines. So if you have, say, 3 straight lines in a certain scale of an image, and you downsample this image in a naive way by just ignoring half the columns and half the rows. Well, these 3 lines, because of aliasing, could be broken down. You know, they could look in that strange pattern that aliasing brings. And then these new lines, these invalid lines, could be considered as corners in these points that they are broken down. So aliasing, generally speaking, changes the overall behavior, the overall nature of an image. and then you could create new corners, you could destroy corners that were actually there, okay? So it depends on what aliasing is going to be doing with your image, but since it changes the image, it will definitely change the corners that you find as well. Okay, so it looks like there's another question here. Can you reiterate the different types of error surfaces and how they match different image features, lines and corners? Okay, I'm sorry that I'm only reading it now, Ellison. So let me see here. Reiterate the different types of error surfaces and how they match different image features, lines and corners. Okay, so let me go back here. Okay, Alison, so first, what this surface means, okay? So this surface is showing us how the error is changing based on the displacement in the x-axis and in the y-axis, okay? So if we are in a corner, sorry, if we are in an edge such as this one, if you change the position of this window and then subtract the values of the displaced window with the original one, and this displacement was in the x-axis, you see that the error is going to not change because the intensities didn't change, okay? So this is what this surface is showing for this particular type of edge, okay? It shows that if you have a particular position in V, so let's say that it's fixed in the y-axis, but you're changing the position in the x-axis, so if you're moving it horizontally, the error is not going to change. So for this kind of edge, the error is going to look like this. But if the edge was being now considered for a window in this position, now it would be the other way around, okay? So in this case, if you change this window vertically, so if you're changing V, nothing happens. But if you change U, even if just a little bit, the error is going to change. As you can see, for a fixed V, if you change U now the error is changing. But for a fixed U, for example, this point here, you could change V as much as you want, and the error is going to be exactly the same, okay? And then if you follow the same line of reasoning, edges are always going to look like this. So edges that are forming a line are going to look like this in the error plane, okay? Flat regions are not changing much, right? The error, regardless of if you're moving in the X or Y axis. This is why they look like this. And corner regions are going to look like a dot, because if you move in the U or in the V, so X or Y axis, you're going to have changing errors, okay? Okay, so question about the midterm. Up until what point are we going to cover to the midterm? Okay, so I'm still, I didn't finish the midterm yet, you know, so I have most of the questions from it. I would say that all the topics until the spring break, so all the topics until Thursday, and maybe some topics from the first class before the midterm. But you know what? Before starting the first class after the spring break, so not this Monday coming, the next one, right? Before starting the class, I'll let you know if the topics in that class are going to be covered in the midterm or not. In fact, I'm going to talk to you about the midterm in this class before it, so don't worry about it, okay? But definitely most of the midterm is going to be given, if not all, by the classes up until the spring break, okay? Would you please give us sample midterm questions? Okay, so this is the first time, Elmira, that I'm teaching this class, so I don't have midterms from past years. I can, let me see. Okay, so I'll discuss the midterm on the first class after the spring break, and then I can maybe show one or two questions just so you can get a sense of the style of the questions, okay? So I don't have midterms from past years because this is the first time that I'm teaching the class, but I can definitely try and illustrate how the questions are going to look like, okay? All right, so another question. In these lectures, where we will look at pipelines. Could you give us example implementations in Python or pseudocodes like the one you gave us for the histogram equalization? I think that is very helpful, especially if we had to use them, if we had to use libraries to accomplish them. Okay, so that would be a great idea, Cristiano, you know? So calculating SIFT features, calculating histogram-oriented gradient features, these are all extremely straightforward when you're using libraries. In fact, they are just one line long, you know, it's just calling a function that was already implemented. So implementations are all about understanding the algorithm. Okay, so if you understand the algorithm, you can go ahead and implement them in Python, etc. Using them with the libraries is it's given, you know, it's very straightforward. As I said, just calling a function. In fact, at the end of assignment 2, I ask you to compare your histogram-oriented gradient features, the ones that you manually implemented, with those implemented by a Python library. So I would say that the best way to do it, first, we have some time constraints, right? But I think that the best way to do it is to understand the steps of the algorithm so that you can implement it if you want. And calculating them, as I said, it's extremely straightforward. We're talking one line. So that will be fine. I can show illustrations, you know, on how they look like. And of course, I can explain how we got to them. But I think that in terms of implementation, they are already implemented, okay? So it would be only a matter of putting into code everything we discuss in class. And I guess this is it. All right. Thank you, everyone, for being here. And I'll see you all on Thursday. All right. So have a nice week. Bye-bye.